All right, thank you all for coming to AstroFest. I've been here several years myself. This is one of the primo facilities in New York for amateur astronomy anything. So join, support it, do whatever you can do for it. So black holes and gravitational waves, it's really nice to be able to say that there's been some really profound stuff happening in astronomy and astrophysics in New York that doesn't just include Cornell. So as it happens, just to get this out of the way quickly, so Syracuse has a contingent of the LIGO group. This is the group running all these gravitational wave experiments, as well as a nice supercomputing facility that runs a lot of the calculations. And my peripheral involvement there is basically using up other people's LIGO time, sadly. But what are you going to do? Like Tish, I'm a NASA Solar System Ambassador. NASA, go. There you go. I run a local club in Syracuse called CNY Observers, basically just doing public lectures, outreach, and everything else. Syracuse.com and NewYorkUp.com, or Upstate, wanted to have a monthly article about stuff happening in astronomy in New York. So if somebody walked outside in the middle of nowhere, what would they see? And so that articles are ongoing. We're on month 4 to good reviews. So if you have any interest in arguing points, by all means, check out the articles. And with that, we'll just jump right in, because sadly I got to leave by about 6-ish. What are we going to do? Okay, so why is this whole gravitational wave just super exciting to physicists? And this is the only way I can think of it. You've all seen these videos on YouTube where a kid hears for the first time, or an adult hears for the first time, and they break down crying at this, and then you break down crying, and the people in the audience break down crying, so I decided not to show that video. But basically the fact of the matter is that we've never had the facility to detect gravitational waves. We knew they were there. It's like other people telling you, I can hear this, I can hear that, or I can see color, and you just would have no concept of what that was. And then to finally have that turned on would be like taking our regular 5 senses and being able to add all the other senses that we have evolved out of ourselves that other animals still have. So this is really big. This is basically a brand new way for us to study the universe, and we're fully expecting to find things we've never found before, new physical phenomena, and everything else to come out of these ability to study gravitational waves. Get that fly out of there. Now, there was a gravitational wave talk about a month ago here, and this is one of these things where you can get really in the weeds, and we can have the full pocket protector debate about the meaning of the physics. And I've got no idea where people's aptitude are, or how much they've read about black holes or gravitational waves, or where your math is, everything else. So I'm going to keep it reasonably basic, and then if any questions come up, by all means, just fire away. But to kind of give a tweak from the last gravitational wave lecture here, I'm going to start a little bit of context. So a brief history of the nothing. This is, how have we kind of identified what there is and what there isn't, and how has our understanding of the universe changed such that we now can have a mathematical model, in this case what we call space-time, into which these gravitational waves and black holes and everything else exist. So how has this changed in the last 3,000 years? So we go way back to the beginning. There are no kids in the room, but back in the day, you'd have to do this thing called film and send it out to this guy who only existed from here up in a box outside of a phase. But you're outside in the middle of nowhere. You see that all the stars of the constellations don't move with respect to each other. You see that there are bright spots, the planets as we know them now, that do move with respect to the background stars. And we know that here we're moving through air. We breathe in, we take things out. Fish move through water, some kind of fluid. It made logical sense, 4,002 years ago, that there must be something there through which everything is moving. This was properly formalized by Aristotle in his, back in the day, this is the physics they had. So the 4 natural elements under which everything that he conceived was made. So the earth, wind, the fire, and the air. Everything else fell into this thing called ether. And some people spell it E-T-H-E-R. I'm going with the old school, the other ether. This was the material, the substance, that which was filling all of space, through which everything else seemed to move in his celestial sphere model of the universe at the time. And this is what made intuitive sense for the physics they could do and the data they could collect from their observations. That something had to be moving through something, because everything on Earth that we know of is moving through some material itself. Now we skip ahead 15 or 1600 years or more. Evangelista Torricelli, who was a disciple of Galileo and one of his assistants towards the end of Galileo's life, who was fascinated by something that Galileo was convinced didn't exist, and that is a vacuum. So Torricelli invented the Mercury barometer, which is to say that he took a tube of mercury, turned it upside down into a bowl of mercury, and found that something up here, which everybody said you couldn't have, existed. They said, this is a vacuum, an absence of something. Now, was it just filled with this ether, but everything else was gone from it? Or what was there? But the fact of the matter is, it was something that nobody said could exist at the time. And he was kind of the first person to show that the vacuum might be a real thing. Jump ahead to Blaise Pascal, who's most famous for Pascal's triangle, probably, for elementary mathematicians. But he had used the barometer, taken from Torricelli, to show that not only do you make a vacuum in a pool of mercury in a bowl, but there's an elevation dependence there as well, which is to say the higher you go, the more space exists inside that tube. And this is poorly shown in these two pictures, but that's the basic idea, which is to say that the further up you go, the less air there is. And if the air is going away, what happens to the air? I mean, what is above the air? As things get thinner and thinner, what is that material? What is that thing, the rest of everything else, into which the universe exists? The notion of the ether. Now, as it happens, the ether existed, this concept of an ether existed well into the 19th century, and was only really fully taken apart very early in the 20th century as a thing that probably didn't exist at all. But for the time being, we really had no proper physical understanding of anything except the Aristotelian view. And this was formally changed by, of course, Isaac Newton, who gave us our first rounds of physical laws. And gave us these physical laws kind of in the absence of these needs for ether or some other material except for forces causing the motions of objects. And so this is just a quick compare and contrast between Aristotle and Newton for these ideas. Aristotle, like attracts like. A rock falls to the ground because a rock and the earth are the same kind of thing. And the smoke rises because smoke and air are the same kind of thing. And it makes intuitive sense if you have no understanding of basic physics, which they basically didn't. But when you actually throw proper mathematics at it and have a uniform calculus which you can define everything against, you can develop very fine laws that explain everything to reasonably exquisite detail for the ability of them to measure at the time. But you see, it's just a fundamental shift in how everything was defined against the old school versus this new school that came about. And of course, there's two very basic equations that most everybody learns in kind of that first semester physics. F equals ma, the ubiquitous F equals ma. And of course, this idea of the law of attraction between objects, this idea that forces exist between any two masses, against which he defined everything else as far as planetary motion, the simple motion of objects on the Earth. You look at the equation, you go, okay, well, you need two masses, and you need to know the distance between them. And then you have this thing, this gravitational constant. And so you can imagine back in the day that of those who were very, full of the notion of ether as this material through which everything moved. Well, if we've defined everything there is in the universe, but we know this ether must exist for things to move through, this constant, this is a number that falls out of a very basic equation. And the question is, where does this constant come from? And so there were arguments way back in the day that, okay, maybe these constants we're seeing are some kind of manifestation of this material or this thing through which all everything is in the universe is moving through and existing. But Newton didn't need that. He could say that there are fundamental constants, but Newton's only concern was how, not why. So his only concern was the fact that there were forces that, for instance, allowed you to explain why planets go around the sun, that there's a force drawing the planet towards the sun, and the momentum of the planet carrying it in a direction. And basically it's these two perpendicular forces that keep the planet moving in a near perfect circle, depending. Didn't need a concept of an ether. He just needed the mathematics and the notion of these forces and basic equations to explain everything. And of course, very different from Aristotle's view, which said that light objects fall slower than heavy objects. When you can make a large enough vacuum, you see that Newton's explanation of just basically the masses of objects and the forces and this constant gravitational force between any object, and in this case the Earth, everything falls at the same rate. You can trust it. The amount of energy to make a vacuum that big, significant. But we didn't pay the power bill. This is a British special, so we can go from them. Okay, that is my very basic idea. Just before we get into the fun stuff, this is that we exist in something, and this something was defined as ether. And we think of Aristotelian's views as something you can teach, younger children, and they go, well, that's kind of crazy now, but at the time, from the observations they could do and the studies they could make, That was the view of the universe, and then Newton basically cracked all of that significantly and changed physics fundamentally and basically stopped good physics for about 200 years, as people said, how do we come to grips with what this 22 to 25-year-old guy had done to explain everything that was going on? And now we get to the fun stuff. And I will preface this, what's going to come next, to make sure that everybody knows what Doppler Shift is. Because this is the beginning of the end of this notion of ether and this need to define where things are moving in with respect to something else. So we all know Doppler Shift. Something flies towards you quickly, the sound wave gets compressed, goes higher pitch. As it goes away from you, lower pitch. I'm not going to accost your ears with any more of that video, but okay, the Nicholson-Morley experiment. These are two of the bravest people in the history of physics, as I will go into briefly. These guys wanted to know the dependence of the speed of light on our direction and our motion around the sun and in the Milky Way, which at the time of 1887 was the entire universe. So they had a very simple experiment. Actually, I will show you the experiment first. This is a basic setup of the device. As you will see when we get to the LIGO discussion, remarkably familiar setup. A light source, two mirrors perpendicular to each other, and a collector. And the notion was, just like with Doppler shift, if the Earth is moving through the universe, actually I'm going to skip 2 more slides to make it easy. Basic idea of what's going on. The sun moves through around the Milky Way. If we're moving through this luminiferous ether, as they had defined, and again, this is a concept that right up to the 1880s, 1890s, was still the medium through which light moved, because light being a wave needed to oscillate through something. Moving around the sun, okay, if the Earth is spinning, or revolving, and the sun is moving in the Milky Way as well, if we're existing in an ether, just like Doppler shift, there must be some change in the frequency of light, depending on the direction that you're moving. So if you're moving against the stream, like a trout going up the stream, you're going to change one frequency. If you move down, you're going with the ether, or you're moving against the ether, and the frequency should change, depending on where you are around the sun in your motion through the Milky Way. And so that is roughly shown here. The concept of ignore all the math. You start with a light source and a beam splitter here. So you got one beam that goes up and one beam that goes sideways. If everything is perfectly still, and these 2 mirrors at the very top and this side here are exactly the same distance, the 2 beams that are split here are going to bounce back and come back down here and constructively interfere, so add to each other, which is to say that you should see a higher intensity here. Whereas, if one of these mirrors is moving, in this case if this is moving, and again moving because we're moving, you're going to get a shift in these 2 wavelengths, and all of a sudden they're going to deconstructively interfere, or they're just not going to have both waves and troughs lining up with each other. And that was the basic thought. So if we have these light beams set up just right, and the light is moving through some kind of ether the same way that we're moving through the air, we should be able to see a difference depending on where we are in orbit, if we're going with the stream or against the stream, or if we're moving into the ether or out of the ether, or in one direction versus the other direction. And of course, to do that, they had this system where they bounced the beam many, many times to get a very, very large effective cavity to do this experiment, which again we showed here. And again, the moving thought. So if nothing was moving at all, the red and the blue would hit the splitter, bounce back to the detector at the same exact time. But if we were moving like this, then there should be a difference at the time with which, in this case, these 2 photons hit the detector. And again, this would be because we are moving through some kind of material which would be affecting the speed, just like Doppler shift works with the way that we hear sounds. And after all that experimentation and many, 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 many trials, they get this figure. The black line is the measurement. The dashed line is the theoretical expectation of the shift in the speed of light, or again, these matching of these 2 photons going into the detectors. And this dotted line is represented here at 1/8, I believe the number is, the expected value, just to have them plotted properly on the same level. So this should be 8 times more than they actually measured experimentally, having done this experiment over and over and over. And now I call them the bravest physicists because everybody expected this luminiferous ether to be this material through which light oscillated. They do all these experiments, and the data they get is totally counter to this expectation of this ether existing through which everything moved. Just imagine doing an experiment 100 times and getting the result you don't expect at all, and the result that nobody would expect at all. And you say, how are we going to publish this? We're going to send this to a journal, and they're going to go, you guys did something stupid. Several years ago at CERN, or the Large Hadron Collider, somebody had determined that neutrinos were going faster than the speed of light. And this was a big to-do for about 2 months until somebody realized they'd plugged in the wrong cable or there was a loose connection. So you can imagine, and this is why whenever, like for instance, the gravitational wave announcement, it took them 4 or 5 months to do the actual announcement, because there's nothing worse in this world than being a physicist who says, this happened, to only be that physicist who 4 months ago said that thing happened. What an idiot. So it's one of the things where you always cover your tracks, because you don't want to be the physicist who is basically banished from the grant writing process forever.
Cold fusion.
Yeah, exactly. Every year, more cold fusion. It's like artificial intelligence. We're always 5 years away, and we've been 5 years away for the last 25 years. And so they say now we're on the verge. Well, what kind of verge? Well, about 5 years.
Does everybody involved in that project know that they possibly found it, but they know that it has to be proved before it gets announced, or are they in the dark until they...
For inside baseball, for something this big, yeah, you would never be the graduate student who was allowed to announce this stuff. You could tell your parents when you went home for Thanksgiving, but yeah, you would never...
If you were involved in working on this, you probably...
yeah, again, you would not... you would not want to... Well, it's... I guess even for you to say something that somebody could attribute to you that would be wrong.
Yeah.
So for instance... I knew about the gravitational wave detection about 4 months before it was announced, because part of it was happening at the university, and they were planning the press release. They were planning this huge gala in a big room with a lot of seats and cameras, everything else. And they said, something's going to happen around January. We can't tell you what it is, but it's going to be fantastic. So make sure you're there in January. All right. The LIGO experiment goes back to 78, 76 was kind of was first theorized between three, and I'll get into that after the fact. But yeah, LIGO right now is up to 1,000 people at least, and the number of people, the engineers, the technicians, the physicists themselves, the theoreticians, the computer programmers. It becomes these. Once you get past several $1 million for any kind of NSF or government grant, it involves lots and lots of people. And you'll see from the pictures just how big this facility is. You imagine how many people were involved in just the basic construction, much less the testing and the analysis of the data. But here's Nicholson and Morley, and it's just, this data doesn't make sense, but this is the data that we got. So let's just kind of throw it out there and see what happens. And this was, this was the beginning of the end of this luminiferous ether. The fact that, we knew nothing about what we know now for the speed of light being constant in all directions. They just knew that there was this photons that were wave-like that had to be propagating through something. And this something was, a manifestation of this ether that goes all the way back to Aristotle, of things that we had to be moving in. And, there's one of these spots where physics comes to a standstill. And of course, in the late 1890s, this is a very famous story that physicists were telling students don't go into physics, because we'd already solved everything to a couple decimal points. And we're really kind of just fine-tuning a couple things here and there, but we don't expect anything new to happen in physics. So don't spend your time getting a doctorate, go into a real science. And of course, Nicholson-Morley comes along. Other experiments, the equipment gets sensitive enough to be able to do experiments that show that there's problems with our current understanding of things. And then, long story short, everything begins to fall apart until somebody like Newton comes around to basically explain or provide a model into which everything else is properly happening. And this is, of course, general relativity was the major transition in physics in the early 1900s. which turned all this ethereal nonsense and all these, in this case, forces from Newton into this concept of space-time, or our modern concept of space-time, because the combination of space-time has always existed in our understanding of the universe from Euclid back on, but this is a full, proper understanding or model of how the universe works, making gravitation as just an explanation of its curvature of space-time, providing a fantastic model for how this stuff works. And of course, you've all seen some of the animations.
Things moving.
I'm going to turn off the Brian Green and hope that the video starts. Oh, but it's not. Oh, come on now.
It's buffering if not moving.
No, it should be. It's a PowerPoint snafu that happens intermittently. There we go. So no longer these arrows of forces between objects that Newton described, but now we see everything as everything with mass causing a curvature in space-time. And everything within these curves, like the moon in this case, moving in straight lines, but moving in straight lines on a curved surface. And of course, the more massive objects sitting in deeper gravitational wells, or in this case, causing greater curvatures of space-time.
If you're a light going through that warp, does it have to speed up to meet the same point? It seems like it has to travel further in a warp space to end up in a spot on the other side at the same time. Seems like it has to speed up. I don't know if it works that way.
No, this is one. This is one of the questions. Start getting into the weeds. This is more the. It's one of these. It's. I can't do it proper justice, I guess, in 5 minutes.
You're looking at 3 dimensions and asking a 4-dimensional question.
Yeah.
When you say that.
Thank you. Okay. So skipping a lot of relativity, I'm getting in just to the point of the black holes themselves because of the significance towards the discovered gravitational waves. But the theory of black holes, go back to the late 1700s. A guy named John Mitchell was a kind of amateur physicist who, working through Newton's work, said, well, we know that everything falls towards massive objects. Could you have such a massive object that everything would fall towards it, including light itself? And one of these kind of, there was no math behind this. It was just kind of one of these theoretical, digressions in a paper, that if you could have something so massive that everything would be drawn towards it. If you've ever seen Einstein's general relativity equation, the basic equation, it's like F equals ma. It's an elegant, tiny equation. And then, like all good relativistic equations, as soon as you try to solve it, it becomes totally unwieldy. Back once Einstein first published the general theory, people began to throw just the most simplistic kind of approximations at the equation they could. So if you imagine here, back in the, with Newtonian mechanics, you could determine where a cannonball was going to land with reasonable accuracy. And the more calculations you did, you could get a high precision on where the ball was going to go. But then, how do you account for the temperature of the air? How do you account for the speed of the wind? How do you account for the shape of the ball? Is it a perfect sphere or a golf ball? The more of the actual reality you try to include in these equations, the more unwieldy the equations become. Schwarzschild had come in with a very, very simple approximation to try to solve a very basic version of general relativity by taking, in this case, an infinite mass with infinitesimal volume, the most simplest case you could imagine mathematically, to develop a model of what has become a black hole. Now, Schwarzschild published this first. Einstein said, okay, well, this is a legitimate solution to the general relativity equations. But as it happens, Einstein did not believe in black holes. So this was a solution to the equations, but you can imagine given an equation, there's plenty of ways to get really non-physical answers out of it. But this one at least worked mathematically. And this was kind of the proper beginning out of a general relativity model of what a black hole was. So, a picture of a black hole. So what do we know about black holes? Not much. We know they're a region of space-time, and the gravitational pull is so strong that nothing can escape, including light itself. From the mathematics of many physicists, from the early basics of general relativity about the 50s or so, we know that basically something with a mass of 3 or 4 stars, or our suns, would be enough to naturally form a black hole. And we know this is where Hawking made a lot of his big beef. We know that right now the theory says that black holes actually evaporate, which is to say that over time you can form, it's a quantum mechanical phenomenon of making virtual particles, which is to say that the energy around the black hole, you can make virtual particles, and one of them may fall in one side of the event horizon, and one will fall out of the event horizon, which is to say that you'll have one particle going out and one particle going in. They evaporate at exceedingly low energies and temperatures. So in this case, a sun-sized black hole might be into the nanokelvins, a ridiculously small amount of energy. And the background energy of the universe right now is about 2.7 Kelvin, which is to say that the universe right now is still too warm for us to even be able to measure properly a radiating black hole. So it's expected that they will evaporate, but we're saying 10 to the 100 years as a reasonable number. And it's just imagine, so 10 with 100 zeros after it, years, before the last black hole will evaporate and the universe will basically just be an empty space of absolutely nothing. And of course, we have our modern model of the black hole, the singularity at the middle, which we know nothing about, the event horizon, the point at which anything on this side gets drawn in, the victim of space-time at that curvature. Anything on the outside can get out. If you want to step further back, there's a thing called the Ergo Sphere, which is where space-time itself is being ripped around. So you can imagine when you pull the drain out of the water at the edges is still getting drawn in and drawn in, but there's a region around that where you can still move through at slower than the speed of light. So the Ergo Sphere is a region around which you could still move and get away from the black hole on the edge of the event horizon. Now, we had lots of reasonable evidence, but still indirect evidence that black holes existed at all. And this is a fantastically famous image from 2004 from the UCLA Galactic Center Group. These are stars at the center of the Milky Way, around Sagittarius A. We didn't know what was there at all. We just knew that there had to be something so massive that stars were being thrown around at the same way that the planets are thrown around the sun. Again, these are false color versions, but still these are the points of stars mapped over, in this case, several years. Now, the original estimate for the black hole was, I think, 2.6 million solar masses, and then once they finally had one star make a full loop around with it and get really good data, they re-evaluated and determined there was 4.6 million solar masses. So only a factor 2, which isn't bad for physics, I guess. And of course, they've refined this significantly. So these are, again, points of stars in the center of the Milky Way. And over the course of several years, these stars just get shot around this point in the middle. So very convincing evidence, not necessarily of a black hole, but a massive, massive object which was releasing no light whatsoever. Which you say, oh, it's basically a black hole. Now, that by definition, it's what we know of as a black hole nowadays, but it still wasn't proper evidence of there being, again, the black holes, there's singularity within the horizons, we've thought about it, but something very massive there, the important part. And I found this on YouTube to play, because this is a fascinating little video. Describing some of the largest black holes, there we go, in the universe. So if you take our sun to turn into a black hole with a solar mass, it would crank down to about the size of a city. So again, 99% the mass of the entire solar system is basically in the sun, and you would have to crunch all of that down to something down to the size of Manhattan, or take the Earth down to a peanut. And here, another black hole. And again, this was totally theoretical until this gravitational wave experiment. We just knew that something like a black hole could exist and probably did exist, but we didn't have the direct evidence. So videos like this now actually make proper, full-on physical sense. Or at least we can say we're not lying when we generate the images.
You say that was in the center of the galaxy?
Yeah, I mean, the expectation now is that every large galaxy's got a supermassive black hole in the center, and which was totally hypothetical and theoretical until, we have a basic understanding of the need for a massive object in the center to kind of direct everything.
Is that the same thing as known as Sagittarius A?
Yes.
Like that, yeah.
Yep. So again, we had the indirect evidence and the expectation from the physics that said, okay, it probably exists, but we'd had no direct evidence before this whole gravitational wave experiment came in. But again, you need to have something supermassive that's giving off no radiation. And it's like, well, how can you have both of them except in this case, except by the explanation with black holes, we all know them nowadays. I love this one. So this is one of the Phoenix cluster black holes, one of the largest ones we know of. And this video just goes on and on and on. But wait. But wait. You just go. It's not worth watching. It's so so zany. And we all came out of a singularity, which is the worst part. We all, as much mass as we all originated from there. It's the best as the theory goes. So we now have a good idea of what black holes are. We still don't have the proper physics to explain them because it happens. Quantum mechanics and relativity, neither one of them right now do black holes justice. They're at the point at which all of our known physics breaks down. And that being said, when we think of space-time is still a mathematical model into which we perform, in this case, general relativistic calculations to explain what's happening. But for the time being, there is, like everything else in physics, there's probably this additional underlying theory which will reconcile all the problems we have. But again, black holes have been a worst-case scenario for a very long time, and we still don't have a proper math to explain what's actually happening. But we know that you can curve space-time with massive objects. So what happens if things are actually moving? And the answer to that is, if you can get two massive objects to move, in this case around each other, you should create waves in space-time, what we call gravitational waves. Now this is interesting. Again, I'm a quantum physicist by training who does a lot of optical materials work, but you take the electromagnetic spectrum, in this case we have the low frequency stuff all the way down to buildings, the very high frequency down to cosmic rays and gamma rays that kind of cover the whole gamut of just sizes of all the matter we know. As it happens, gravitational waves actually work under the same kind of spectral condition. We can describe them very similarly in their waves. And so we have the cosmic background at these lowest frequencies, high frequencies. We have our interferometry equipment, like our LIGO facilities here. The space interferometers, again, once you get away from the shaking Earth and the atmosphere and everything else. But basically, gravitational waves exist over this entire spectrum, the same way that we have a description of electromagnetic waves. So it happens, and I have a demo. If you're reading anything about black holes or gravity in general, you'll hear that mass couples very poorly to gravity, which is to say that gravity is a fantastically weak force. And it's weak enough where a couple simple ball magnets, in this case one ball magnet, is canceling the gravitational pull of the entire planet to keep this small magnet attached to the other small magnet. So gravity is an extremely weak force that only works over very large objects. And as far as you think of, in this case, space-time or gravitational waves, if you have a symbol, the people closest by me can hear it, but I've got to get it up to a pretty good rate before anybody behind me can hear it. And gravitational waves, as we discover, are basically the same thing, given how poorly matter and gravity couple. So if you beat on an object extremely hard, with enough force, then you cause these proper oscillations, in this case space-time. And so this is the notion. In order for us to get gravitational waves that are significant enough for us to be able to detect, you have to have massive objects interacting, causing massive ripples in space-time, and causing these massive gravitational waves. So to get back to the history a little bit, so this is a Calvi Prize. So I forget the guy's first. So Calvi is one of these super rich people who wanted to do something like the Nobel Prize, and so has begun awarding prizes in astrophysics and nanotechnology. This was a prize from, I think, a year ago. Again, Drever was a guy who developed kind of this high sensitivity for optical equipment. Rainer Weiss actually had this idea of developing an interferometry, like that Nicholson-Morley experiment thing, for studying gravitational waves as it was a graduate physics question on an exam, was where he started it from, and decided this could probably actually work, and began to develop the technology of developing massive interferometers which would be sensitive enough to detect gravitational waves. And of course, Kip Thorne, everybody knows him from Interstellar, among other things, and his interesting debates with Stephen Hawking. But kind of the primary physicist behind the study of gravitational waves. And again, these three are the basic foundation of LIGO generally. So when the Nobel is awarded next year, it will probably go to these guys, depending on the politics of selecting other people. People expected it this year. I mean, this is profound enough in physics where it's kind of like Obama winning the Peace Prize for not being George Bush. People expected that this was solid enough where the Nobel Committee would absolutely select these three for the winning the Nobel this year, but they didn't, which means they will probably get it next year. But the basic experiment is just like the Michelson-Morley experiment, just many, many, many times larger. So I'll wait for the video to go through this basic part first. Okay, so your laser source goes to the beam splitter. One wavelength goes out, bounces off fantastic optics. The second bounces off, they come back to the splitter. In this case, they're meeting destructively, so both peaks would be subtracting, so the effective here would be 0 for how these two are combining. But if one of them is moving in any direction, those two waves are going to wind up sliding. They're either constructively or destructively, so constructively, destructively, constructively. So either you're going to get signal or no signal, depending on how these peaks are lining up, or the waves are lining up. And that is really, it's as simple as that, as far as the equipment's concerned. So just to get the basics down, so the first experiments were done at LIGO Hanford and LIGO Livingston. GEO 600 is now online, and there are 3 more in the process of getting completed. But basically the first measurement they got on September 14th was just from the 2, Hanford and Livingston. And then for Nicholson and Morley could have done their experiment on this tabletop. Here, as it happens, each one of the tubes for the interferometer is 4 kilometers long. As it happens, 4 kilometers is nowhere near the sensitivity. It gives them nowhere near the sensitivity. So as a matter of fact, the light here is basically being bounced roughly 200 times. I think it was 170 for the first LIGO and 190 for the new LIGO. So the effective tube length here is about 1,000 kilometers, which would be much harder to build. So this is the Livingston. Again, that's the Hanford. And then for scale, these are about 4 meters or so. So I mean, just imagine going to the government for a grant. So we need to build 4 kilometers long. It's going to be 4 meters or so tall. Take up an unwieldy amount of space. And then again, here the center is the business end of the interferometers themselves. So just physically, this is a massive, massive construction. But after everything is said and done, they get the sensitivity of this particular interferometer down to 1 part in 10 to the 21st. I did the math already. So you take the center-earth distance of about 150 million kilometers, 1 part in 10 to the 21st, 1.4 times 10 to the 10, or 10 to the minus 10 meters. Converted to nanometers, 0.149 nanometers. The hydrogen atomic radius is only 0.12 nanometers, which is to say that if you had the sun of the Earth and you displaced their centers of mass by 1 hydrogen atom radius, they could detect that with this interferometer. That's how sensitive they needed to be be able to detect gravitational waves under the theoretical expectations. That was what they needed to achieve in the interferometer to get the sensitivity. Another number I've heard thrown around is us to Proxima Centauri, the closest star. If the Earth shifted 1/10 of a micron towards Proxima Centauri, that would be the sensitivity they could measure at 1 part in 10 to the 21. Unbelievable. Another one, and this is a video from the LIGO people themselves, if you take a meter stick on the table, for them to do their 1 part in 10 to the 21, if this was a hydrogen atom, we zoom in, we zoom in, we zoom in, well into the nucleus, 10 to the minus 15 meters or so, this would be the oscillation they would have to measure. They would have to see the proton do that. That's the sensitivity they needed in this interferometer to detect gravitational waves as they were first calculated, their first expectations, their first theoretical limits for the thing to work at all. Unbelievable sensitivity. People can do fantastic things, is the short answer to that, when they put their mind and their money to it. And so what ended up happening was, on September 14th, a day or so after they turned them on for actual production runs, this is a theoretical version of what was happening. Again, 2 black holes, and again, we're counting down by the hundredths of a second here. Starting about a 350 kilometer distance for the 2 of them is where this whole thing began, of 2 black holes in gravitational lock to each other. And then over the course of hundreds of seconds, then we get down to the thousandth of seconds as the simulation goes. Point emerging, and then you can see the ripples just going out. Again, this is a two-dimensional, like everything else, this is a two-dimensional projection of what's happening. But that's the idea. And then basically they settle down to nothing in particular. And there's another idea of what was happening, just so you can see the full effect of lensing behind. If you could see it against a proper backdrop, and you could slow down everything enough so you were seeing hundredths of a second of resolution. Again, the important thing is once they actually do merge, you just see this ripple go out as kind of the last thing you see. And of course, this was the data they actually got. Now I'm going to turn the volume up. I'll play this again. I'll play it one more time. It's that last little popping sound that is the final interaction of the two in the formation of the gravitational wave that we measure. If you've ever gotten these cheap ball magnets at a store somewhere, if it's not you doing this, it's really annoying, but if it is you doing this, it's fascinating. But you separate them by a distance, and you throw them up. I know, it's great. It's the same basic idea. I'm hearing it first, people in the back of the room are hearing it last. Depending on how you separate the balls to begin with, you're going to change the frequency, you're going to change the shape of this little whoop at the very end. But that's, and if they're too far away, they separate from each other. But, this is kind of the most basic way you can describe this to anybody else as far as the difference in the shape of these trip sounds that they hear when they're actually measuring the gravitational wave going by us. And I'll stop and I'll keep it far away from my laptop. You never know.
So this is speeded up.
This clicking, the clicking sound?
Not the clicking are the tenths of a second, right?
Oh, yes.
And then that little whoop?
That's real time. No, that's real time.
That's real time.
Now, it's real time from 2 black holes, one of them being, well, as we'll get to the slides, we're talking 2 black holes that are better than 20 solar masses. So I mean, we're talking basically 20 times the mass of the solar system in each one of these black holes, spinning around each other in fractions of seconds, finally combining.
Actually, you can't hear it first because it's too low in frequency for your ear to hear it.
Right. It's
At the end, you can hear it.
Yep. You're either causing very, very low frequency. It's basically below your hearing threshold. If you can make a sound at 1 hertz and then crank it up and then crank it higher and higher and higher, and at some point it becomes audible. And in fact, what they could do is they could take this and they could just basically plug it into a speaker, and they could hear the chirping sound. I mean, this is the actual sound you hear of these two black holes coming together. And again, this is the data slid to merge. Again, the inspiraling, the merger, and the ring down. The ring down being, again, that's just that final release of energy, which, not to scale, and I'm glad they qualified this, but this is the basic idea. This gravitational wave deforms all the matter. Again, we're talking about, the fraction of a proton's, radius motion, but...
Could there be some kind of catastrophic effect from this?
No. Thank heavens. Again, here's the final data, and this is a great slide, because for all relativity and every year somebody tries to say, Einstein, well, I got him on this one, and I got him on this one, and no, he's wrong here, and here's a final flaw in relativity. And they're always shown to be full of it. The yellow line here is the theoretical prediction from general relativity, just basically throwing the numbers at a supercomputer that you can grind away at, and here's the actual measurement from Hanford, and here's from Livingston, and the theory is right on top. Now, you think about this. You've got two interferometers separated by a couple thousand kilometers. 1 in 10 to the 21 sensitivity on a thing which is on the ground, where the Earth is moving, shaking from, just tectonic plate activity. You've got large animals going by which might affect the sensitivity. Just imagine everything you've got to do to cancel out everything else on the planet which would cause any motion in this equipment. You've got to account for that somehow. And they could do it. So when you see all this kind of, this jumbly noise, I mean, you're literally talking about, fractional heating of some of the mirrors affecting the sensitivity of the equipment. But, from what they could do, it's just amazing the quality of the theory and the experiment that you get when you put them both together. And not only that, but with 2 of the interferometers, we have at least a ballpark idea of where in the universe this merger occurred. And again, this is, put the picture up here. It's 2 milliseconds between LIGO or Hanford and Livingston at the speed of light. Or 10 microseconds rather. And they got a 7 microsecond difference between the 2 chirps, which is to say that they know that the chirping sound had to come from somewhere, if you could, poorly figure it out from space, somewhere that wasn't directly in line with Hanford and Livingston, because that would have been a full 10 microseconds, but to get 7, it's got to be coming at some shallow angle. So this is just basically, once you've got a third one of these interferometers set up, you can do the full triangulation to determine more or less where something is coming from in the universe. But with only 2 of them, you get this very kind of guesstimated idea of error bars of where you think it's coming from. So that third interferometer is going to be very useful for pinning down where things come from.
Background is our galaxy on that one?
Yes.
Okay.
So, by that being said, what we know about, in this case, this gravitational wave, again, 15/09/14, so 2015, September 14th. The first direct evidence of a binary black hole merger. All the math works. You need to have 2 massive objects combining to cause this kind of a ripple. 1.3 billion light years away from redshifting. The mass is 36 and 29 solar masses of these 2 black holes that merged. Spinning at 75 hertz, so 75 times a second. And the resulting black hole was about the size of Iceland, if everything was said and done. And the final mass was 62 solar masses. And those of you who are good at arithmetic are going, 36 plus 29 is not 62. This happens this merger lost 3 full solar masses of energy. You needed 3 full suns converted into pure energy to cause a ripple large enough for us to detect here with a the interferometer that has a sensitivity in 1 part in 10 to the 21. And again, we get this conversion just from E equals mc squared. Now, as it happens, 3 solar masses for the amount of time that this merger occurred, you take all the visible light from all the stars in the universe for the same amount of time, and you multiply that by 50. And that's the amount of energy that was released in this merger of these 2 black holes to cause a ripple in space-time that we detected with an interferometer, barely detected with a sensitivity of 1 part in 10 to the 21st.
Did you know these 2 existed before the event?
Well, no. They literally had this data about a day after they turned. So they had been testing and testing and testing. And they said, okay, we're finally ready to start looking for it. So they turn it on, and then about 1 day later, they get the first signal. And so which tells you lots of things. And we'll in the next slide. So again, 3.6 times 10 to the 49 watts of event power for the whole thing. Now that being said, on October 12th. They got something which looked about right, but they didn't have really good data for. But on December 26th, they found one that was a merger of a black hole with solar mass 8 and solar mass 12, significantly smaller than the 29 and the 36. And as it happens, this one they estimate about 1.4 billion light years away, or 1.4 billion light years ago, which is to say that these events are probably happening, all the time in the universe. But we never had an ability to turn anything on to listen or to see or to use any brand new senses from what was actually happening. So now we actually have a piece of equipment that's letting us see mergers of black holes or other massive objects, which is the big point. So we're going to be able to detect more and more. So basically these things are happening all the time, and now we have a way to hear them. And so the expectation is probably 6 a year or so we'll be able to detect. And then now that this has worked, the first thing you do after you make a sensitive piece of equipment in the laboratory is you make a more sensitive piece of equipment. That's the name of the game. So once you've got it working and you can show the granting agencies that it actually did work, and we now have, we've again validated another part of general relativity and the first direct evidence of black holes. Now you say, okay, come back to us next year, we'll write you another big check. And you just fine-tune the equipment, and you continue. So now we should be able to see neutron-star mergers, black hole neutron-star mergers. So basically, it's one of these things where any object with mass causes a gravitational ripple. You need to be a black hole or more to be of any significance. I mean, it's one of these things where you say, yes, an atom moving in theory causes a ripple, but there's no way you're ever going to see that ripple. Everything does, but you have to qualify that you still need to be massive at this point for us to be able to see anything. Now, imagine when we get this into space and get away from all the problems of measuring things on Earth, how much more the sensitivity is going to be. Will we be able to see stars, colliding? Who knows?
Comets colliding with planets.
Really close.
That's good.
If they're right now, if the comet's hitting us, maybe. But, and again, so this December 26th one, you can see there's a much less agreement on where it might be. I mean, it's definitely wider, but imagine once that third interferometer is running and you can properly triangulate, life becomes significantly easier. And then we're going to have 6 of them running on the planet. And so we're going to have that much more fine-tuned data. And at this point, will we discover brand new physical, phenomena, new objects that never existed before that we couldn't see? Maybe. The next 10 years may be profound for redefining, again, more of physics. And again, we are still trying to get data sets which let us reconcile relativity and quantum mechanics. Part of that is mathematical, so the physicists and the theoreticians can fight, but part of this is just more experimental data. And so we will begin collecting more and more and more information about the universe that we can throw into, newer and newer models, newer and newer definitions. It's possible that, we will live long enough to see a more general theory of the universe or of existence itself come out of additional data, and we have no idea, but
But as long as these things are black holes, we'll have no other verifying data. Right? We can't see them.
Yeah, well, we don't. Before this, we could only see their influence on everything else.
Yeah.
And actually, in the 70s, there was indirect evidence for black holes and gravitational waves from pulsar studies, but it was still very indirect and not exact, and certainly not quality data enough to be able to say anything profound. I mean, a black hole is a massive object that doesn't radiate. Well, it's tough to say, is that just a massive object, or is that an actual, just break in space-time? It's, just how do you define what a black hole is without any other data? And now we actually have a way to get data, which is extremely exciting. So we'll see again, they expect to see more and more as years progress. We will build more sensitive interferometers, and we'll see what happens.
How about if on the largest scales, looking at the universe as a whole, after the inflation period, or if you had, let's say, call it an oscillating or jittering universe type of thing, is there a possibility that there could be a product end of that type that would enter into the picture, or we can't talk about the large scale?
If you're meaning the residual ring, of that, if there was, again, just this, like setting off a chirping sound in a room, you're going to get all the echoes and the bounces. And I guess the question is, right, and it's, at some point the universe gets large enough. So, right now the background radiation is 2.7 Kelvin. And then the longer we wait, the lower the temperature is going to go because, again, it's just, everything's getting redshifted in space-time expand. And it's, I guess, we don't know if again, this is more of a cosmological question, but it's, I guess the question is, how big would those waves be after the first event? And then will we ever get the sensitivity to detect those? And have we gone, in this case, 13.8 or so billion years, have we gone too far for them to be so small now that we will never have the sensitivity to detect them? I don't have an adequate answer, even to the base question. But it's again, one of these things where it comes down to sensitivity again. And so again, the more sensitive we get, it's tough to fathom, hitting 10 to the 1 part in 10 to the 23 or 24. But you just imagine, at some point we're going to, how much more we can detect, and then at some point you have to say, how much can we explain of what we're actually seeing? Can we resolve it down to local stars, or can we resolve it down to smaller black holes, or again, other phenomena which we have no idea even exist yet?
Now, these pictures, this picture right here.
Yes.
Did this actually come from the direction of the Milky Way, or is that just?
Oh no, that's just where in the sky it is.
Oh, it is where in the sky it is.
Oh, but it's, we're still talking, 1.3 or so billion light years infrared, right? So it's, but looking that way, one of these thoughts is, after you can detect these things, you can tell the observational astronomers, go look in that direction, see if you see anything. Because you'll see the first ripple, and then you'll see anything happening after that. So everything will have to be quick. But again, once that third interferometer is up, it's going to make the observational astronomers will have that much more to work from.
So right now, you've got two intersecting cones to form these solutions. Is that
Yes.
And the distance is determined by the intensity of the signal?
Yeah. It's a basic redshift.
Well, redshift.
Well, it's I guess the equivalent of redshift. It's
it's inverse square, right?
Yeah, but plus the expansion, just the expansion of the universe anyway. And so it's the same way that you could take the equations and say, okay, that galaxy is 1 billion light years away because we see a redshift of this from the stars that we typically see anyway. And so it's the same basic idea.
What's the speed of gravity?
It should still be the speed of light. That is still our upper limit. And in fact, it was
used in all the calculations then right now?
Say that again?
That's what's used in the calculations, Joe?
Yes, yeah, it's I have that. I got to put the slide up.
I don't need to know,
No. It's,
I wondered if there was a supposition as to what it was.
no, as far as we know, this is one of the extra slides.
Theory shows that it moves at this.
Yeah, it's the information. Yeah, it's anything involving information. Again, position. Oh, I'm going to stop that now. Everything is still governed. The speed of light is still the limit. And again, this was the major transition from Newton to Einstein in some respects. That Newton believed that gravitation was instantaneous, which is to say that he had to believe in this static model of the universe, which is that every star is exactly where it's supposed to be. And if one star nudges a millimeter in one direction, it's going to instantaneously change the nature of the interactions between everything else in the universe. So everything has got to be static, permanent, and having existed forever. And that was one of the bases of Newtonian mechanics. So he said, okay, if it's instantaneously interacting, it has to be having infinite speed, so nothing can really move from its base location. And no massive object can move significantly, so no two stars can get too close together because it's going to change the whole dynamic of the system. And then Einstein comes along and goes, okay, everything's happening at a speed. In this case, it's governed by the speed of light. And so now, of course, we get into the whole cosmological constant, debate, and Einstein's thoughts of the universe was, impermanent and existing forever, or actually started from the beginning, and this is a completely different discussion. But yeah, everything is still governed by the speed of light, or everything happens at the speed of light. As it happens, that was my base closing thought. Again, I apologize for the compression and for the people who are here in 3 hours who aren't here to ask me any proper questions. But any additional questions, I love talking shop, so Damian at somerville.com, or just go to cny.org and sign up for the email list and get track of all the updates and observing we ever do. If you don't keep track of any articles, I do not discuss anything black holes because the editor said do not go into any crazy physics. They said find where the stars and the planets are and leave it at that. But it'll be New York Upstate or Syracuse.com. And thank you guys, again, for Copernic and for coming to the lecture. And I'm going to haul out of here very quickly.
Thank you very much.